In today's lesson, we are going to be looking at the quadratic function. This should be a review from last year in grade 10. We're basically just going to be looking at an overview of the different types of functions that we could have and some of the key characteristics of quadratic functions. So the first key characteristic of a quadratic function is the shape that the graph or the function makes when you graph it. In this case, it is a parabola. So the graph of a quadratic relation is called the parabola. It's generally formed by this U shape, or it could be inverted and have an N shape. But there are a few key or important features. So we do see them here. First big one we have is our vertex, which we'll again talk about more. We have a y-intercept, so it should cross the y-axis at some point. It has the x-intercept as well. In this case, this quadratic has two x-intercepts, which is okay. That is an option that we may have. And we also have something that is called an axis of symmetry, or AOS. So those are some of the key characteristics of a quadratic function, specifically of a parabola when we graph it. So again, just some more information about a parabola. In general, a parabola can open up or down. So what we mean by opening up, if we look at an example or a sketch of the last graph of our parabola, so it looked like that. The opening was facing up, and we also mentioned that it could be inverted, where the opening would be facing down. So when we're talking about opening up or down, that's what we're referring to. The zeros of a parabola, so this is a new term, is where the graph crosses the x-axis. So zeros are just another word for x-intercepts or roots, which we do see in that space below. So we'll just go jump quickly down here and highlight this. Just some other terms for zeros. So zeros, again, are where the graph crosses the x-axis. And depending on our graph, there could be 1, 2, or 0 zeros, or x-intercepts. So depending on your graph, you could have 1 x-intercept, you could have 2 x-intercepts, or you could have no x-intercepts. All three are possible depending on your parabola and your quadratic function. Again, we mentioned that zeros can also be called the x-intercepts, which you might be more familiar with, or roots, which is also another term for x-intercepts. So the blank divides the parabola into two equal halves. This is a vertical line right up the middle in the form x equals and blank, and that blank is going to be the x value that it crosses at, or that it goes through. This is basically the definition for our axis of symmetry. So the axis of symmetry is that vertical line. Now you're not going to see it on a quadratic function. It is kind of an imaginary line that you wouldn't draw in there. It's a vertical line that goes right down the middle, and it has the equation x equals and then whatever x value it goes through. The vertex of a parabola is the point where the parabola changes direction. So where it changes, if we're heading down and then we start to go up, or if we're going up then we start to go down, that point where it changes is the vertex. It is the point where the parabola is at its maximum or highest, or minimum or lowest value. So the vertex is also at the maximum or minimum point of our parabola. This is also the point where the parabola and the axis of symmetry meet. So because this is that point where it changes direction and the axis of symmetry is a vertical line that cuts our parabola in half, they would meet. So the axis of symmetry is going to go through our vertex. The optimal value is the y value, or is the value of the y coordinate of the vertex. So if we ask for the optimal value, we're talking about what is the highest y value or what is the lowest y value. We get that from the y value of the vertex. And the y-intercept of a parabola is where the graph crosses the y-axis. So again, just understanding x-intercepts, it crosses the x-axis. Y-intercept, it crosses the y-axis. From here, we're going to look at some different versions of the quadratic functions. So we are going to look at the 3 different versions in depth later, but we're just going to do a quick overview of the different forms as well as what information there may be in there, or the forms may have. So the standard form, if we see an equation y equals ax squared plus bx plus c, this is the standard form for a quadratic equation. Now, there's really only 2 key pieces of information or 2 pieces of information that this equation will tell us about our quadratic function. First, it is a. A tells us the direction of the opening. If it's positive, it's up. If it's negative, it's down. It also tells us the step pattern. And we will touch on the step pattern a little bit later. The c value tells us the y-intercept. So there's really not too much of this, too much information from this, from the standard form. It tells us the direction of the opening and the y-intercept. It doesn't really give us too much other information. The factored form, this is what we will look at this in the near future. The factored form, y equals a times x plus r times x plus s in brackets. So in this case, the a value is the same thing. It tells us the direction of the opening. Again, plus, if it's positive, then it opens up. If it's negative, it opens down. And it also tells us the step pattern. The r and the s values, tell us the roots, or it tells us the x-intercepts. But we want to be careful because it's not exactly as we see it. So it is the opposite of what we see. And specifically by opposite, we mean opposite signs. So actually, let me just rephrase that. Opposite signs of what we see. And it tells us the x-intercepts. So in this case, because it's a positive r and a positive s, the 2 x-intercepts, and again the x-intercepts are when y equals 0, would be negative r and 0, and negative s and 0. Again, in the actual equation, these letters would be filled in. The y and the x wouldn't be filled in, but the a, the r, and the s would be. So the biggest thing about the factored form is that it does tell us the x-intercepts, where the graph crosses the x-axis. In our vertex form, y equals ax minus h squared plus k, this tells us some different information. You might be able to tell from the vertex form or the name itself, but this form will tell us the vertex. But looking at it, let's go through and find out what each one does. So again, the a value, you might have guessed, the a value tells us the exact same thing. Direction of the opening. Positive opens up, negative opens down, and it also tells us the step pattern. The h value again, it's the opposite of what we see, or sorry, opposite sign of what we see. And it tells us the x value of the vertex. You could also say, because it tells us the x value of the vertex, it also tells us the axis of symmetry. So the AOS is going to be, we mentioned it previously, will have the form x equals, in this case, the value will be h. So whatever our h value is, and see here we see it as a negative, so whatever the positive h value, or the opposite of what we see, is going to be our axis of symmetry. The k value, it's exactly as we see it. We don't have to worry about opposite signs or anything like that. The k value tells us the optimal value. And when we're talking about optimal, we're usually talking about max or min. So the optimal value. And it also tells us the y value of the vertex. So the h, or the opposite of the h value that we see, tells us the x value of the vertex. The k value, as we see it, tells us the y value of the vertex. So in the vertex form, we get the actual vertex of hk, right, of the coordinates h and k. So the nice thing about the vertex form, it does give us that vertex point. So each form, or each version of the quadratic, or of the quadratic functions that we see, gives us different pieces of information. Right? They're all useful depending on what we may want to see, or what we're trying to find. And throughout the course, we will learn how to convert between all three. Right? So hopefully by the end of the course, we're able to convert between all three different forms of the quadratic function. But for right now, we're just going to look at each of them individually. In this lesson in particular, we're just focusing on recognizing that there are three different kinds, and each kind gives us a different piece of information. Moving on to the step pattern. So this is something that appears in all three formulas, or all three types of functions when we're dealing with quadratics. So the general formula for the step pattern goes 1A, 3A, 5A. The A value comes from the formulas. So the A value that we're talking about here comes from the formulas. And essentially this means 1 times A, and then 3 times A, and then 5 times A. And it's not a coordinate, it's basically just a set of numbers, a list of numbers. Right? So 1A is one number, 3A is another number, 5A is a third number. And these numbers tell us how to find, or how to plot points of our quadratic, or of our specific quadratic function, from the vertex. And so the steps for that would be, if we have the vertex, we go over 1, up 1A, so whatever that value is, whatever 1 times A is, we go up that amount, and we plot a point. For our next point, to plot our next point, we go from that point we just plotted, we go over 1 again, and then we go up 3A, or 3 times A. We plot another point. And then from that point, we go over 1 again, and we go up 5A, or whatever amount 5 times the A value is. So using this step pattern, that allows us to plot other points on our graph. Right? It helps us make a little bit more accurate depiction of it. Right? If we had just the x-intercepts and the vertex, we might be able to sketch it, but we wouldn't get an accurate representation. So here we can see a more visual version of this step pattern. We have our vertex at the bottom. Use a better color. We have our vertex at the bottom, 4, -6. We have our step pattern from the equation, or this a value, right? So if we rewrite it, ax minus h squared plus k, that's our general form. So we can see the a value is 2. So that means in our step pattern, it would be, again, the general form 1a, 3a, 5a. So that means with this a value now, 1 times 2, 3 times 2, and 5 times 2, which would then simplify to 2, 6, 10. And we see those numbers appearing on this graph already, but again, let's just kind of walk through how it works. So we have our vertex. We take one step to the right, and then we go up 1a, which in our case, 1a was 2. And you can see here we've gone up 2. From there, we go over 1 again, and then we go up 3a to our next point, which is, we go up 3a, which is 6. And we plot our next point on the grid. And then finally, from that point, we go over 1 again, and we go up 5a to our last point. Up 5a would be up 10 in this case, which we do see here. So 5 times 2 gave us 10. That tells us on this third step I go up 10. And then I have 3 points. Now it doesn't matter which way we go, because I can go in the left direction over 1, up 1a, which would be 2. And I see I have an exact mirror on the other side. I go over 1 again, and I would go up 6. Or 3a. And then finally from that point I would go over 1 again and up 5a, or up 10. So it doesn't matter if you go left or right. Again, with a parabola, it is symmetrical on both sides, and the step pattern shows us how far up we go every time we move over 1. So it gives us an idea of how to plot a few more points on our quadratic, right? We may be able to just plot the vertex, maybe the y-intercept, depending on if we convert it to factored form, we would be able to plot the x-intercepts, but this allows us to plot a few more points, right? So this is just an example of just explaining what the step pattern is. But the main thing from this is just being able to recognize the different components of a parabola, know those kind of key features, the vertex, the x-intercepts, the y-axis, the axis of symmetry, and recognizing that we have 3 different types of quadratic functions that we will be looking at, and each of them displays different information or has different information that may be useful depending again on what we want to look at. So again, just understanding that there is a variety of representations or types of quadratic functions.